Hi everybody, welcome back to the channel. Let's go ahead and take a look at an example using integration by substitution with a definite integral. I just wanted to see one example here about how to relabel your bounds and make sure that we're just careful and rigorous in the work that we're doing. So let's go ahead and take a look at an example. We're going to look at the integral from 1 to 2 of dx over 3 minus 5x squared. And you might want to keep in mind that another way to write this is the integral from 1 to 2 of 1 over 3 minus 5x squared. Oh, well, got to write it the right way though. Squared on the outside with the dx on the end. So same thing, whether you want to put the dx up in the top of the fraction or on the end. And so we can look at how to be able to handle this. Notice inside your function is a linear function, and when we identified earlier an inside function, what we said is, does the derivative of the inside function also show up on the outside? And remember, in our last example, we could have been off by a constant or coefficient there. So if you call u your inside function of 3 minus 5x, then what we end up having is du dx, the derivative, is equal to negative 5, and this is just a constant. So even though there's no other values that show up on the top or out front or anything like that, the fact that we just get a constant for our derivative means we could be off by that constant or that coefficient to start out with. That's okay, we can still be able to handle this. So get du all by itself, and this means we have something like negative 5 dx on the right side. And I'll remind you that you might want to consider relabeling some of this stuff. We're going to have something like, I'll tell you what, let's go from up here. We could relabel this as the integral from 1 to 2 of, let's see, this would be 1 over u squared. And then really all we have left is just dx, right? There's nothing else really even with that dx. So what I would recommend you doing is over in this du equation, try to get dx all by itself. In other words, go ahead and move that negative 5 over to the other side. You could either write it as negative 1 over 5 du, or you could write it as negative du over 5, just as one fraction. That's fine. Either way. Okay, and that's equal to dx. So we are going to replace a dx with a negative 1/5 du. And again, just like in the last video, it doesn't really matter that 1/5, because that 1/5 you can just move that out front. And in other words, this is negative 1/5 times the integral from 1 to 2 of 1 over u squared du. Now I wanted to be a little careful here in how we label things, because technically we got to be pretty careful here with our bounds, and I haven't been so far, but let's take a look at what I mean by that. Because the 1 and the 2 right here, I'm going to put them in red just to say warning here, be careful. This 1 and this 2, those are actually talking about x values, aren't they? Like in the original, we could have written from x equals 1 to x equals 2. But technically x now, after we've done the substitution, x isn't even our variable anymore. Okay, x isn't 1 and 2 because we don't even have an x in here. Now we just have a u in here. So really when we have the bounds, we should be consistent. If we're going to have a u in the problem and then have a du on the end, then our bounds here should actually be the bounds on u, not on x. Okay, so we probably shouldn't have a 1 and a 2 there. Let me go ahead and rewrite these, and we're going to change these just a little bit. And so we've been doing substitution in here, and we've been replacing a u, and we've been replacing an x and a dx. We also should be thinking about, in a definite integral, be replacing the values of the bounds, because those are not x values anymore. They need to be values of the variable, which now is u. Okay, so here's how we're going to do this. What happens when x is 2? Okay, I'm going to say u of 2 over here. Go ahead and find what u is when x was 2. All right, well, when x is 2, u is, let's see, 3 minus 5 times 2. So u would end up being -7. And go ahead and do the same thing and create a little space here. Go ahead and do the same thing when x is 1. So what is u of 1? Basically, we're going to replace the lower bound and the upper bound that used to be x values with their respective u values. When you plug in u equals 1, you're going to get something like, let's see, this would be 3 minus 5, so -2. And so really, u then is going from -2 to -7, okay? And we're replacing them on the same places where they came from. So in other words, when x was 1, we're replacing the 1 with a -2 because that's u when x was 1. So even though I know that -7 is less than -2, it's not always kind of lower to upper there. We got to replace them where they came from. So here it's -2 to -7, and so on and so forth. Now there's a couple of different ways you can handle this, because now what we're going to do next is we're going to actually take the integral of 1 over u squared. That's kind of where we ended up right here. I know there's a lot of work on the screen. So what we have at this point now says we're supposed to have -1/5 times the integral of 1 over u squared du, but now our bounds go from -2 to -7. Okay, this is where we're at, and basically we've substituted from x's to u's to hopefully make the problem easier. Now I know that we had to replace a dx with a 1/5 or a -1/5 du. That seems like that one made it harder. We had to replace the lower bound and the upper bound from x's to u's. But if you look at what's actually inside of the integral right here, that piece is a lot easier to deal with than what we originally had. Okay. By the way, just as a reminder, another way to write 1 over u squared, you could go ahead and write that as u to the -2, and then think about a power rule. Okay, so this is going to end up being something like -1/5, and then let's see, this would be u to the -1, and then you need something out front that's going to cancel out that -1 from dropping down. You get something like this, and you could either evaluate this from u equals -2 to u equals -7. And you could go ahead and plug in -7 and plug in -2 and subtract, just like we would have back with our fundamental theorem of calculus part 2. Or what you could do, and this is why ultimately it doesn't matter too much, if you were to go back to x's, then you can actually still keep your bounds as your x's. I mean, you shouldn't, as far as being technical here, but if you replace everything with a u back with having an x in it, then you end up getting something that looks like this. You have u to the -1, by the way, is 1 over u. So you could have -1 over 3 minus 5x, and then you're not talking about from u equals -2 to u equals -7. Now you're using those x values again that we had in the original. So then we're going from x equals 1 to x equals 2. And subtracting. So you could either do it this way, or you could just plug in and think about using plug in -7 in for u, and then plug in -2 in for u and subtract. Either way, you'll get to the same place. So just something to kind of be careful about. Okay. So let's see, we end up getting something like -1/5 times -1/7 plus 1/2, if you go ahead and plug those in. Again, either one. And I think you end up with an answer. I'm kind of skipping a couple of steps here. I think you can follow the arithmetic. So just at this point, it's just kind of combining some fractions together. And then at the end there, I think you should get something like 1 over 14 as your answer. Okay. So again, the substitution here said take a difficult problem at the beginning that had x's in it in the integration. Because you had a function whose derivative, or at least off by a coefficient, but close to the derivative, showed up on the outside, you could replace what was in the inside. You could replace the original dx and get stuff in terms of u that was an easier one to integrate, and then be able to plug in from there. And again, you could either substitute back into the x's from the u's and then plug in, or you could, it's probably easier just to think about plugging in -7 and plug in -2 in for u, and then combine from there. Okay, so just wanted to see one example using a definite integral with substitution. Very similar to an indefinite integral, but as I said in the last video or a couple videos ago, definite integrals always take a little bit more work, a couple more steps, because you can't just stop when you get the function at the end. You actually have to go plug in b, plug in a, and then subtract and find a value. So notice we got one number at the end, not just a new function with a constant of integration. Okay, hope you've enjoyed. Hope this kind of clarifies or solidifies some of the stuff about substitution.